Okay. Hi, my name is Okoro Reginald Chidera. I'm the team lead for the air quality monitoring analysis, an interactive outshiny dashboard built on 1,845 sensor observations across 6 pollutant variables. Over the next few minutes, I'll walk you through the data, the dashboard architecture, and the key findings, including a 30-step forecast for where pollution levels are headed. Here is the roadmap. I will cover the project objectives and the tech stack, the data set itself, how the dashboard is structured, the descriptive analysis, the AQI category breakdown, time series, and correlation analysis, the forecasting model, and close with the key findings and recommendations. The core objectives was to monitor urban air quality across 6 pollutant indicators and build a real-time interactive exploration tool, not just a static report. Specifically, the project set out to identify temporal and seasonal pollution patterns, analyze how pollutants correlate with temperature, apply ETS time series forecasting with a 30-step horizon, and classify every region into an HY category for public health insights. The start with R and the shining for the core app, the shiny dashboard for layout and navigation, Plotly for interactive chat, DPRYR for data cleaning, the focus package for ETS modeling, and DT for the fragmented data table.
Hi, my name is Jonathan Kamarachi, and I'll be taking us on the data set description. Here, the data set covers 6 continuous pollutants and environmental variables, where we have the carbon monoxide, the nitrogen oxide, the nitrogen oxide, and ozone, PM2.5, and temperature, plus an ordinary AQI category, ranging from 1, which is good, to 4, which is unhealthy. On preprocessing, mixing values in the raw sensor data were encoded as -200. We replaced those using DPLYR, imputing column means across all numeric fields. That left a clean final data set of 1,845 complete observations across 7 columns. No missing data going into analysis. Looking at the dashboard architecture, here, the Shiny app is organized into 5 interactive tabs, where the Overview tab has KPI value boxes for average, max, and mean, a pollutant trend line, and a distribution histogram. The Time Series tab shows a full area chart with field to 0 plus a carbon monoxide versus nitrogen oxide dual line comparison. The Correlation tab features an interactive RDBU heat map across all 6 variables and a scatter plot against temperature. The Forecast tab runs an auto-fitted ETS model with a 30-step ahead forecast and a 95% confidence ribbon. And here, the Data Table tab is a paginated scrollable table. All of this is driven by sidebar controls, where a pollutant selector and an observation slider, which filters life from 100 up to the full 1,845 records. Looking at the slide 6, which is the descriptive statistics, are the summary statistics across all 6 variables in sensor raw units. PM2.5 shows the widest spread with a standard deviation of about 280 and a range from 773 up to 1,948.03, which is the most stable, with a standard deviation under 120. Temperature here has the highest mean at 2,246 but that's on the sensor's own scale, not degrees. These baseline numbers are what everything downstream, which is the AQI classification, the correlations, the forecast, which is built on. Thank you.
I'm going to be talking about AQI category distribution. Breaking the 1,845 readings into AQI categories, 32.2% or 595 readings fall in the good category. Clean air conditions about a third of the time. 27.9% or 515 readings are moderate. The sensitive groups category is the smallest at 10.6% or 195 readings, short spike events. But the unhealthy category sits at 29.3%, 540 readings, which is nearly 30% of all observations. Put together, sensitive and unhealthy, that is categories 3 and 4, they account for 39.9% of all readings, and that is the headline number. Almost 4 in 10 readings in this dataset represent conditions that are potentially harmful to the human health. Now, moving on to the time series analysis. On the time series side, the dashboard tracks peaks and cyclic behavior over the full observation window. Peak carbon monoxide hits 1,266 and peak nitrogen dioxide reached 1,388. The overall pattern across pollutants is cyclic rather than random, and it is consistent with recurring daily or weekly emission cycles, which becomes important later when we get to the forecast. Now, onto the correlation analysis. The correlation heat map is where the combustion story becomes clear. Nitrogen dioxide and nitrogen oxide correlate at 0.98, which is expected, since nitrogen oxide is essentially the total oxide family that includes nitrogen dioxide. Carbon monoxide and nitrogen oxide sit at 0.97, and carbon monoxide and nitrogen oxide at 0.94. These three move together because they share the same source, which is traffic and combustion emissions. Ozone and PM2.5 correlates more moderately with the combustion group, which is in the high 0.8, but temperature is the outlier. Its correlation with every pollutant hovers around 0.10 to 0.15. In other words, pollution levels in this dataset are not meteorology driven. They are driven by emission sources, not weather. Now, talking about forecasting. For forecasting, an ETS model was used, and ETS means error, trend, and seasonal. It was auto-selected through the R forecast package with a weekly frequency of 7 and a 30-step ahead horizon at a 95% confidence interval. As expected with any time series forecast, the confidence bands widen the further out the prediction goes, reflecting growing uncertainty. And this is applied per pollutant, and it is switchable live through the sidebar selector. Now, to close, nearly 40% of readings fall into unhealthy or sensitive categories, which is a real public health concern. Carbon monoxide, nitrogen dioxide, and nitrogen oxide correlate above 0.94, pointing to the sheer traffic and combustion sources, while temperature plays almost no role. The ETS model forecasts a gradual downward trend in CO over the next 30 steps, and the cyclic weekly pattern lines up with workday versus weekend traffic. Based on that, I'd recommend targeting emission controls at traffic and industrial combustion, building an automated AQI alert system, expanding sensors to include PM10, SO2, and meteorological data for casual modeling, scheduling weekly ETS retraining, and ultimately deploying the app publicly for citizen and regulatory access. Thanks for watching.